Okay, well, let's get started while the rest of the group gathers. Let me start off by telling you I want you to wash your minds of anything you currently know about fusion. I'm gonna tell you what I think is important as we go along, and I think you will agree that what you currently know is probably not current. Now, let me start a little bit with a background. My father was born in horse and buggy days at the end of the 1800s. He lived long enough to fly on a jet plane and visit Hawaii, actually before I moved there. So he didn't visit me in Hawaii. One of my earliest memories is riding on the back of a horse. This was not a riding horse. This was a plow horse. My father was following along behind that horse, plowing the field with the horse. He raised squash and corn and beans and tomatoes that he sold as truck crops to the market, and that was our livelihood while the orchard was growing. We grew up in Southern California, 70, 100 miles south of here. The reason I bring in this background information is that it gives you a little bit of an idea that I grew up in a very different world than the one you live in, an energy poor world. Horses were our energy source. I can remember my mother cooking on a kerosene stove. Our refrigerator was not a refrigerator, it was an ice box. Now, I'm not that ancient, you understand, but we didn't get electricity on the farm until the mid-30s. The house was originally plumbed with acetylene for lights. So we had gas lights. It was converted to electricity. My great-grandparents built the house in 1929. Now, why do I bring this up? Because we've lived up until now, or certainly I have, in 100 years of the most abundant energy ever available. And unless you have fusion, it will be the period of time in which the most energy per capita was ever available. The reason is, I'll show you later, I'm a geologist, by the way. I know a lot about energy. I guess I should tell you a little bit more about myself. My background started off in physics at Caltech, undergraduate, and bachelor's and master's degree in geology, however. I discovered geology and found it a fascinating topic as an undergraduate. I took my PhD at Princeton in geology. Subsequently, I've taught at Caltech, at University of Texas, Dallas, and at the University of Hawaii. I retired about a decade ago, and although I had previously been the director of the Hawaii Institute of Geophysics, the oceanographic arm of the university at that time, I was the director of Sea Grant at the time I retired, and I went back to work after I retired for a year or so as the vice chancellor for research. But a few years ago, I got involved in fusion. Fusion has been one of those topics that has been fascinating me since undergraduate days, when I used to race over from Caltech all the way over to the Nevada test site to watch the A-bombs go off. They would announce at 11 o'clock at night that a bomb was going off the next morning, and we would literally race all the way to the test site to see the bomb go off the next morning at 5 o'clock. That's a long-winded explanation of where I'm going. I used to drill oil wells when I was your age, or in college at least, for Soil Oil Company. And I've stayed with the energy industry ever since. I'm well versed in energy resources. I used to work in geothermal energy as well as in oil, and now fusion. So let me go forward and begin to give you some idea of where we're going and why. When I grew up, there were 2 million people on the earth. There are now 6.5. We're headed for 9 billion by the middle of the century. Those are numbers that you've been told, and they're likely to be true. But I want you to notice where all the red areas are on this map. The red areas are those areas where people live. That's population density. And on the next chart, I want to show you where the energy is consumed. This is a map courtesy of NASA. And you can see where all the energy is consumed, and it's not where the people live. You will see that Southeast Asia is red, very red, but on the energy map, it's very dark. Same is true for Central Africa, same is true for some of South America. Much of the earth population does not enjoy the energy availability that we have. And if we don't do something about our energy future, we will enjoy the same situation as the rest of the earth, dark. And that's why we're talking to you about fusion. You have to have a new energy source during your lifetimes to replace what you now use. That has to happen. It can be nuclear power plants, or it can be fusion. Those are the only two choices you have. The energy is the fuel of national prosperity. If you'll study this a little bit, along the bottom we have the gross domestic product per capita. That's how many thousands of dollars you bring in per year per person. Now, that's average for the country. That includes all the children and the retired folks. The vertical axis is the gigajoules per capita. Now, a gigajoule means nothing to you, probably, but 6 gigajoules is a barrel of oil. So, if you wish, divide that by 6, and that's barrels of oil. 60 barrels of oil is what you consume, each of you, to maintain your lifestyle. 60 barrels of oil you do not have in a decade's time. That's the message, the bottom line message. And you can see that we and Australia, because we're both distributed populations, use the most of energy. Other countries are more compressed populations, they have more public transport, and they use less energy per capita and still enjoy a reasonable gross domestic product per capita. This is the projected world energy demand. And what I would like you to really notice here, I'll see if I can get the mouse to work. I'll change hands here. And I'd like you to look at this part of the curve. The future. The future projects a growth rate in energy. Why does it project a growth rate in energy when we know we have limited energy supplies? Because that's what the population of the globe expects. It expects to emulate the United States. It can't, but it expects to try. It also means that we grow our population. We're going to increase by 50% by the middle of this century. But what I want you to notice also is over here. Where does all this energy come from? This energy comes from oil, it comes from natural gas, it comes from coal, and a little bit from nuclear power and renewables. 85% of our energy comes from depletable supplies. Oil has peaked. We will never have production of oil as high as we had a few years ago. It's just impossible to sustain. Oil fields cannot deliver that much oil. Gas, we've been drilling 4,000 wells a year in this country, and we haven't increased the supply at all. Uh-oh. I made a mistake. I forgot to turn off the cell phone. Come on, turn off. Somebody got rudely answered and replied to. Anyhow, coming back to these depletable resources, oil has reached its maximum. Gas, we've been unable to increase in this country. We have increased it elsewhere in the world because of the prolific gas fields in the Middle East, but even those have limits. They have the same problems we have. You cannot continue to produce gas at the rates that a well initially comes in. It declines at about 10% per month. Any gas well does. Coal, everybody says, we have infinite supply of coal. No, not even a 300-year supply, not 100 years. I don't even think we have a 10-year supply at the current extraction rate. I think we'll see peak coal within the next 2 years. A recent article in National Geographic says that peak coal will occur next year. That is an article based upon a professor at Caltech and another professor at the University of Texas at Austin. They have assessed the world's...
Should be straight here.
Sorry?
Remote size, can you please mute?
I don't need that one. I'm not going to roam like I said I was going to do, so. Anyhow, the resources that we have are all depleting, and they're going to deplete more rapidly. That means we have to put something major online, and that major, I think, is fusion. And the mind-boggling thought that comes from that last slide is the following. 14 terawatts between now and the turn of the century is what's required. That's 10,000 new nuclear power plants of average size, typical size. Or it's 18,600 and some power plants, coal-fired power plants, for which we have no coal, or will have no coal. Or 400 new 35 gigawatt electric, what we call heavy ion fusion star power complexes, which we'll talk about in a moment. Every year for the next 40 years, you need to bring on 30 new fission plants or 556 new coal-fired power plants, coal and gas-fired power plants, or 12 fusion facilities. We clearly are starting from a deficit. We cannot build that fast because we have been very dependent upon fossil fuels, all of which are going to peak almost simultaneously. This is my message. The existing sources, hydroelectric, coal, gas, they all have problems. Coal, nuclear, wind. I don't think wind will ever amount to a hill of beans. It will remain small, and production is not reliable. When the wind doesn't blow, no power comes out. Solar is likewise. Everybody's bought onto the solar wagon, but I don't think that's the right answer. You don't get power when the sun doesn't shine, and that means for a week at a time you get no power out of almost any place in the world. That means you have to have a backup. That means the cost is doubly high. Biomass, well, that takes away from food supply. Biomass is, some of it is waste product from growing food. I think you have to go to the only thing that's not on this list, that is fusion power. So my conclusion is that technology is the answer, but it's not these technologies that we're showing over here. We need a large resource, not a collection of small ones. And we need a source of liquid fuels. Our society depends upon liquid fuels. You cannot change society's infrastructure overnight, and you're going to have to change overnight. And fusion is the source we have to use. Now, I told you to wash your minds of fusion, because all the fusion you know about won't work in this time frame. You've been told that since you were grade school kids. Fusion's 30 years away. 50 years ago, 50 years has gone by, it's still 50 years away. It just hasn't happened. Why hasn't it happened? Not because we haven't tried. It hasn't happened because we tried to make it small. Fusion is never small. And so I want to talk to you about the big approach to fusion, and that's accelerator-driven heavy ion fusion. Fusion can be online if you follow that approach. And here's my little joke about 50 years ago. They're in print. And that's because we put our hopes in tokamaks. Tokamaks have problems that scale up with the size of the facility. The problem just gets bigger as the facility gets bigger. It doesn't have a converging solution. There is a way to do fusion today. It was demonstrated in the 1970s. It was all worked out. It was approved by international science bodies, but was never built. And what is heavy ion fusion? Heavy ion fusion is use of an accelerator to drive an ion beam of heavy ions, xenon and lead probably, maybe xenon to mercury. That's a currently known technology. Linear accelerators are a known technology. Ion beam steering is a known technology. We can get two ion beams to hit on cross sections less than the diameter of the human hair. That's what Large Hadron Collider has demonstrated. Pellet fabrication, we know how to build pellets and freeze deuterium and tritium inside a capillary or inside a sphere. We know how to do heat exchange. That's conventional. We do it all the time. There's a better way to extract energy from electricity, make electricity from a fusion power plant, but we're not proposing to use that because it's never been demonstrated. All the technology that we want to use has been demonstrated. It's not experimental. It's all been demonstrated in different applications. We want to see that this demonstrated technology is used for an application of fusion power generation. Here is the scientific feasibility. It was vetted by large committees of scientists back in the late 70s and early 80s. It was reestablished and re-reviewed in the 90s. It was re-reviewed more recently even. It's always received a no showstoppers, go ahead, do it. But no one's ever done it. Why? It takes a lot of capital and it makes a big amount of energy, a huge amount of energy. And you'll see that as it comes up. We need leadership and we need funding. As a corporation, we're willing to provide some of that leadership. Is Google willing to provide some of the funding? Good question. I'd like to talk to some of your leadership about that. The layout is like this. We have an ion source, multiple sources that are then funneled together into a single accelerator because they're ions of different mass. You have to accelerate them differentially to get them all to come out of the end of the accelerator at same magnetic stiffness so they can go around a corner together. Otherwise, they all just scatter as you go around through a magnetic field. You then put them through some delay lines to make sure, take out all the spaces between the pulses that you started off with, because you want this to be compressed. You want all of these bunches of ions that started off as 1,000 separate bunches over here to arrive at the target over here in the same microsecond, same nanosecond. And this can be done, it turns out. This is what the Large Hadron Collider does. We know how to do this. This is not new. It's just apply conventional accelerator physics to a different application. So we show here a series of reactor chambers and the steps that have to be used to get there. And you can think of more chambers over here to the sides. Up to 20 chambers can be powered from one accelerator source. This is a poster that's over on the wall. You can look at it at your leisure. You can't read it on the screen, I don't think. Well, maybe you can. But the main point is that I want to get from this is that we know this is a source accelerator, an ion source. This is the DC accelerator. These are the conventional LINAC sections. We come out the other end, and we either, through these long tunnels, the other end to generators. The only thing we never built is the reaction chamber. It's been designed 4 times, but it's never been built because we had no source to feed it. So it's been designed on paper and thought about. And this little diagram down in the corner here is the flow of energy from the chamber through the various heat exchangers to the generators. But more importantly, there's a fuel component in here. And I want to talk about fuel for a bit because that's what really hurts us in the future, and this process can help. This diagram visually shows the amount of energy coming in, and it's being partitioned off into various processes. This is waste heat going up. These are captured heat and energy going down. And the one I really want you to focus on is liquid and gaseous fuel, the production of hydrogen using the sulfur iodide process, which is a high temperature dissociation of sulfuric acid process. Well researched, but never applied because we don't have a big high temperature heat source. It has to be 1,000 degrees centigrade, that source, and fusion provides that. Liquid fuels are the key to our future energy supply. Fusion allows the efficient production of hydrogen. Almost half of the energy content coming out of the fusion reactor can be captured and converted to hydrogen. The combining of hydrogen with CO2 extracted from the atmosphere does a very interesting thing. It produces methanol. Methanol was used as a gasoline feedstock in New Zealand for more than a decade. They used their source of methanol was natural gas, and using the same process we're proposing to use right here, they used this process. They produced gasoline. You can go on and produce kerosene and diesel via the ExxonMobil and Sasol patented processes. They're used every day, everywhere in the world. This is not pie in the sky. This is functioning chemistry that's going on today. The result is you have a carbon neutral fuel system. You take the carbon out of the atmosphere, you make a fuel out of it, and you put it back in the atmosphere and you burn it. Doesn't solve the part, doesn't take away from what's already there. It just temporarily uses it and puts it back. But it's a carbon-free business in the sense that there is no carbon involved anywhere. There's no additional carbon involved anywhere in our process. And you have a carbon-free energy for electricity, production of hydrogen for fuel cells, etc. Let me give you some idea of the size and scale of such a facility. One heavy ion fusion facility can produce 500,000 barrels of oil per day. That's the production of a giant oil field. Think of it. You can build a giant oil field wherever you want one, anywhere in the world. Your materials to feed it come from ocean water. Deuterium, that's where it is. It's in the oceans. About a 1,000,000-year supply of it at our current rate of consumption. There's no refining required because you've built it up in the process from hydrogen and carbon dioxide. You made a hydrocarbon that you put in your gas tank. Your car doesn't know the difference between this gasoline and the gasoline you currently burn. The diesel truck doesn't know the difference between the diesel that's produced synthetically and the diesel that you currently burn. Why? Because it's the same refinery process that produces it. It's exactly the same. And the production of such a system does not decline in 5 years' time as most oil fields do. Oil fields come on, peak produce, and then decline, and forever decline at 12% per year. The problem we're having now is that all big oil fields are beginning to decline. Most of our fuel comes from 100 different big fields. There are 4,000 fields that we get fuel from, but almost all of it comes from those 100. And they're starting to decline. You can't recover from that decline. And I guess most importantly from my perspective is what we're proposing as a product, liquid fuel made synthetically from energy, water, and carbon dioxide, supports the currently existing infrastructure. You distribute it by pipelines. You distribute it by gas stations. It ships around in tankers or tanker trucks. You don't have to invent a new infrastructure in order to use this stuff. It's the same stuff you're currently using. And your current cars and trucks can use it today. You don't have to replace all of your rolling stock. That makes a big difference. I mean, I realize we're going to replace the rolling stock all the time. We always do. We're a throwaway society. But you can keep using it as long as you can maintain it. The economics are typical of all big things. There's an economics of scale. HIF is not an exception. There's no question that size does matter. The bigger you make the facility, the more economical it gets. You want to have big facilities because you get low-cost energy. We've put an awful lot of effort into making 1 gigawatt fusion power plants for the last 40 years. We haven't succeeded. You probably never will succeed. Why? Very simple why. It takes a huge amount of energy to get deuterium and tritium to combine, and you want 100 times multiplication or more when you finally get them to combine. You want 100 times as much energy out as you put in. You can't do that with small systems. At most, they'll break even. Most of the small systems will never break even. They're just taking energy from one source and wasting it and giving you part of it back in another source. The design that exists currently and is being pursued by Germany and Russia, the GSI version of heavy ion fusion, produces energy at a higher cost than coal, energy produced from coal. The one that we are proposing, because it's much larger and uses a different way of accelerating that ion beam, which means that you can have much greater yield per unit pulse, is about 10 times more expensive, but it produces 100 times more energy. That turns out to be very cost competitive. It's cost competitive with any fuel, coal, natural gas, any other one you want. But it does take a lot of capital up front, but you get all that capital back within 3 or 4 years. It's even at these low prices of energy, you get all your capital back in a few years' time. I've done these models over and over and over again. I cannot find a flaw in that logic. What I guess want to leave you with is a few thoughts. The solving of the energy challenge that we face as a society requires the understanding of technology and its implications and the implications of that use. We ignored the implication of the use of coal, and the result is we have a CO2 problem. The ocean is feeling that CO2 problem. I don't know if climate is. I can't convince myself that climate has actually warmed, but I can tell you that the ocean has gotten more acid because I measure it constantly on another project. But the consequences of our energy usage are real. As near as I can tell, the only consequence that I can see for converting to fusion is that you have a lot of waste heat to contend with, but it's a much more efficient operation than any other form of generating energy, and therefore, per energy generated, you have less heat emitted. You capture more of the heat into the process that you want to sustain. The requirements for us to proceed are vision and leadership. My hope is that I've given you a little bit of my vision and that you might be willing to learn some more about it and follow that vision a bit. It's going to take leadership from government, from individuals, from corporations, and from philanthropic organizations to make this happen. Philanthropic organizations, in the way I see them, include the NGOs. We have to see that there is a better alternative to the way we currently do things. In my view, fusion is the solution for the fuels and transportation problem that we face, for the electricity problems that we face, for the water problems that Los Angeles faces. If you have waste heat, you might as well use some of it to evaporate seawater and produce fresh water and a brine that you put back in the ocean. And it provides us energy, low-cost energy, to reestablish a metal refining and fabrication industry in this country. We have exported that industry because we did not have low-cost labor and low-cost energy. We consumed our low-cost energy for cities. We need to reestablish that ability to fabricate metals within our borders. The need is urgent from my perspective because I see things from a geological perspective. I understand the decline of oil fields. I understand the decline of coal mines, and I can give you specific examples and industry-wide examples if you wish. But those declines are real. They're going to happen. I can't stop them. You can't stop them. That's the property of a finite resource. Think of this as a predator-prey relationship. The predator is man, and the prey is the earth. Once you consume it, it's gone. You don't have it, and you can't find more. And the time to act on all this is now. It takes 10 to 20 years lead time in order to get one of these online. But if you'll think a little bit about all those renewable resources you now depend upon, and you even put in 4% per year decline, and I'll guarantee you 2 of them will decline much more rapidly than that, you will find you don't have 20 years. You'll be hard pressed within 5 years' time, in my view. I don't like that because that's in my lifetime. And I don't want to be hard pressed for energy. I like energy. I like those 15 slaves that follow me around everywhere that I give instructions by turning on and off the light switch. I mean, that's basically what power is to you. It's 15 slaves or 17 slaves behind every one of you doing your work for you. I leave you with a thought-provoking question as my concluding question. what do you think your standard of living will be in a decade's time without fusion? And I'll be happy to answer questions, and I'll let you read this last slide at your will, if you can read it on the screen. Yes, you can. Okay. Thank you very much for listening. I'd be very happy to answer questions and have a discussion on any of the topics I brought up. Thanks again.
About your methanol from CO2, you mentioned that sulfuric acid used in that process. So where does the sulfuric acid come from? Is that a finite resource?
No, the sulfuric acid winds up being basically a catalyst. You start off with sulfuric acid and iodine, and the reaction between those gives you a hydrogen iodide and sulfur dioxide, and you recycle that back around through the process each time. You could go, if you want to read about it, go to sulfur iodine, and you'll find it on the web. And it's a very well-known reaction, very well researched. It's been demonstrated. There's an operating plant in Japan that it's a glass plant, glass tubing. It's not a metal tubing like you would want in an industrial plant, but it is a very well-known process. It does not consume the sulfuric acid or the iodine. It just uses them as a vehicle to give you a process that you can separate, because the hydrogen iodide separates from the sulfuric acid. They're immiscible, and therefore you can disassociate each one separately and then recombine the products, except for the oxygen and the hydrogen, which you capture and market. There are other ways of getting hydrogen using other processes. They're similarly efficient. High temperature electrolysis, not quite as efficient, but close. Sulfur iodide is the most efficient of all the processes. Yes?
So I noticed that, if I remember right, you said it cost $20 billion to build one? If we set aside like the problems of fundraising and getting capital and things like that, if somebody showed up with $20 billion and said, let's build it today, how long would that take?
It would be limited by the permitting process. You could build it from a construction point of view, it would take 5 years. From a permitting process, it may take 10. But I think in 5 years' time, you'll be so hungry for energy, you'll say, forget the permit, give me energy. I'm sorry for being so crass. But yes.
Could you go into a little bit more detail about that 20 billion capital estimate and the different
The
components
capital
of that?
investment?
Yeah.
Well, the biggest component of the capital investment is the linear accelerator. There has been a recent proposal to build an international linear collider, ILC. You can read about it on the web. They estimated that for a 22 kilometer long accelerator, it's going to cost something on the order of $10 billion. We have said that we only need 1/3 that amount of acceleration, but we need a little bit of fancy trickery here and there, which is going to add a little bit to the cost. So we have used $10 billion as our planning number for an accelerator. The chambers themselves cost about $1 billion each. That's comparable to a chamber for a nuclear power plant. It has a very complicated liquid lithium recirculation system inside the chamber, because without lithium being present surrounding the reaction point, you get problems with the neutrons. We solve the neutron problem that all other fusion techniques stumble upon by having our explosion take place inside of a sphere of lithium. That lithium is vaporized, but not consumed. It is strictly vaporized, and that becomes part of our working fluid, and then we chill it and make another sphere out of it and drop it in and fire it. This is an explosion process. It's like a 60 RPM engine. It sits there and goes bang, 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 in vacuum, so you don't hear it, but it goes bang, 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 once a second in each chamber, and there are 10 of them.
You'd mentioned the chamber earlier as a potential problem. Oh, sorry, I'm over here. Oh, this way? Yep.
Oh, sorry.
Microphone, so I figured I would just
Okay,
go.
the microphone's over there. I was looking over here, and the
All right.
microphone's over there.
So you mentioned the chamber as a thing that's been designed 4 times but never built. And this is the part, you probably answered some of it with the lithium and it explodes 60 times a second kind of thing. So what kind of problems are you likely to run into building that, since it's only been designed 4 times and never actually built? Is that really
Well,
likely to get off the ground?
they are competing designs. Some of the chambers have been designed to maintain optical continuity within the chamber. They've been designed for laser fusion. So you have to maintain optical continuity for 192 beams, very complicated business. In our case, we need 2 beam entry points. Actually, there are 4 beams on each side, so it's 8. We have 8 beams focusing on the pellet, but they come in almost parallel from opposite sides. The chamber itself is largely a vacuum chamber, but it has to be isolated from the world because it has lithium present in it. Lithium reacts violently with water and oxygen and some metals, so you have to be very careful about what you put in that chamber and what you use for pumps. But other than that, it's all been designed and says, yes, it's doable. Now, from an engineering point of view, it's doable. Of course, we've learned a lot about processing of lithium in the last decade, and all these designs were done 2 decades or more ago. Lithium has become a very common substance because of lithium batteries. And as you know, it is a fire hazard, but if you put it inside of an inert atmosphere and inside of inert materials, it's just like any other substance that you have to have a appropriate containment system for it. It'll be operating at about 1,300 degrees centigrade. Was there a question back over in this corner? I saw a hand come up, but
Yeah, so the chamber seems like a big puzzle. So 10 gigajoules is about a 2 kiloton nuke going off every second. So
no,
that's a pretty big explosion.
It's an explosion that is the equivalent of a barrel, 1.6 barrels of oil per second. So it's like a big diesel engine with,
So that's like
with a charge
10
of 1.6 barrels of oil, if you wish.
Yeah, I think, what is a ton of dynamite is 4 megajoules.
Okay.
So a kiloton is 4
Yeah, it's a little over,
gigajoules.
it's a ton or so of explosive
Right.
at a time.
Right, so that's a pretty big explosive. It's hard to imagine.
But remember,
like a-
there are no gases other than lithium, and lithium, as it expands,
I see, so the,
intersects with other lithium and cools to where it goes back to being a liquid, not a vapor.
so
and the
that
explosion stops.
stabilizes every second?
Pardon me?
So that'll restabilize every second in order to.
The calculations say that you can the calculations say that you can run it at 2 cycles a second. We're proposing to start it at 2 seconds per cycle and graduate and creep up on 1.
So what's the scaling limit to build that? Because that does seem like a pretty tricky thing to get right. I mean, could you build like a smaller one to just fire a couple times and?
You can build a smaller chamber, but in reality, you have to contain the explosion.
Right.
You have to have the accelerator. You cannot build anything without the accelerator. It's your sledgehammer. And your sledgehammer costs $10 billion. You might as well put the extra $1 billion on it and make a full-size chamber.
Yeah, I mean.
I would not build 10 chambers
Yeah.
if I were doing this today, as the man over here asked. If you gave me the money, I would not build 10 chambers right out of the gate. I would build one, and then I would modify it to make sure I incorporated what I learned from the first one. But frankly, this is much like building a jet airplane. You don't build a jet airplane and test to see if it's going to fly. You fly it in a computer. You fly an accelerator and a chamber in a computer to find out whether it works. That's how good your computational skills are these days.
Okay. So could you use one of the existing accelerators to essentially build a chamber alongside as a test?
Well, you can't, no accelerator has the Hydra source, the multi-headed source. You'd have to build, you have to build a multi-headed source to go with an existing accelerator. And you'd have to build all that telescoping part that brings all the 16 ions. That you're using 16 different isotopes. You have to treat each isotope separately, because otherwise you violate a whole series of things like Maschke limit and so forth. You violate one of the parameters, but by of physics of accelerators. But by going to multiple isotopes, you have enough degrees of freedom that you can maintain beam quality all the way to the end. So it's really a specialized accelerator. There is one that works with 4 isotopes in Brookhaven, but has nowhere near the length that we need to have. It has only demonstrated the principle of telescoping and shown that it works just fine, but it doesn't have the power that we need.
Good.
We've explored all accelerators in the world. There is no accelerator you can do this with. You have to build one.
Hi, yeah. You had mentioned gathering the fuel from the bottom of the ocean. Can you elaborate about the fuel source itself? I'm a little confused.
The fuel source is deuterium. It is 0.4% of the ocean. It's just a heavy isotope of hydrogen. Every glass of water you drink has deuterium in it. It's heavy water. We used it in H-bomb manufacture, or A-bomb manufacture back in World War II. So it's a known, deuterium is a known issue. The other component of the fuel is tritium. Tritium you start up by getting your tritium from current nuclear reactors, but you also breed tritium in the reaction chamber, because that lithium, the way you get the lithium to take care of the neutrons is you convert part of the lithium-6 and lithium-7 to tritium and helium. So you have a source of tritium that you harvest out of your own facility, and it's the other half of your fuel. You use almost all you produce. Maybe you use a little bit more if you're not careful with your branching ratio. Your imported piece of fuel is deuterium. The rest of it you generate. You have to import lithium. We will be a major user of lithium, and that lithium is currently scheduled to go into electric car batteries.
So
We'll have to find another supply, or we'll have to compete pretty hard. Yes.
So once you have these precursors, you have to form a pellet and for other forms of fusion. The pellet has to be particularly spherical, and that
No.
production process is particularly complicated. Is that persist in this form?
That's that part you're supposed to forget about. The whole round we don't use. It's too complicated to build. We use a lead pipe, literally a lead capillary tube, chopped into lengths, and the capillary is filled with deuterium, tritium, frozen, and you heat the lead casing around the outside of the deuterium that compresses it, and then you impact it on the end with in this case mercury. H came up, but the symbol came up, not the name. Okay, with mercury ions, and that gives you the fast ignition pulse that you have to get the temperature up to 1,000,000 degrees. So it's a two-step process. The ignition is a two-step process. First, compress it. Secondly, ignite it. You can't do that with lasers, because the compression process ablates material off, and you can't get the second beam in because it gets reflected back by all the material that's flying off and gets in your way.
So, but in particular, you're planning on like using 60 pellets per second, and you
Yes.
have to get them into the chamber and so forth.
You're
So
just
the-
dropping 50 of those not per second, per minute.
Per minute, excuse me, yeah.
Yes, you're dropping.
1 per second.
You're dropping 1 per second into the chamber, and they take a fraction of a second to get there because they've fallen part of the way under gravity outside the chamber and the rest of the time inside the chamber. There is a valve that has to open and close. It's nothing more than, as I say, think of it as a great big diesel engine without pistons. The piston is actually well, if you actually get direct conversion going, the piston is a magnetic piston that you actually use to get electricity out. And we don't propose to depend upon that direct conversion route because it's never been researched adequately. We propose to use conventional heat extraction techniques.
So how about civil engineering challenges? Suppose you have a 100 gigawatt facility and it's 70% efficient, then you're basically dissipating 30 gigawatt overall continuously. And
My efficiency calculation is that for the sulfur iodine process, it's about 50% of the heat is converted to hydrogen. So you get 50% efficiency at that point. What's left over is still hot enough to make steam. We use that steam to generate electricity to run the pumps and so forth that are going to have to go on and to be present in the refinery part or the building it up part. We overall think about 60 to 65% of the energy can be captured, a bit more if you're going to have a water maker at the end of it. That is no more of a heat load than a current nuclear power plant like San Onofre. San Onofre puts out a 6 gigawatt heat load.
well, so you have a 100 gigawatt facility.
But I'm extracting over 60 gigawatts of that as marketable energy.
Right. So you have
It's that energy goes into a fuel or into electricity I ship away from the site.
right. So that leaves about 30 gigawatt that needs to be dissipated as heat waste.
I have up to 30 gigawatts that I have to dump at the site. I guess I said it incorrectly. You currently, San Onofre currently puts out 12 gigawatts of heat into the environment. So I'm putting out maybe 3 San Onofres.
Okay.
And some of that will go into water, which I hope to ship away as hot water. Gets rid of more energy. I have to admit, if you air exchange it, you do have a Helium effect that's quite serious. I've had some meteorologists take a look at that, and they look at it the following way, that if you distribute that discharge heat over a 10 square mile area as a series of points, you don't puncture the troposphere. You will produce some rain downstream. There's no question you will produce rain downstream. Unless if you cool in the ocean, different story. But if you cool in the air, then you have a heat load problem you have to worry about. But that's the same problem that the facility outside of Phoenix has, where the 3 nukes are. They have a heat dissipation problem that they have to worry about, and they distribute it over about a square mile. Atlanta has a city of Atlanta has a heat discharge problem as a city. The rainfall is increased on the downwind side of Atlanta. Same is true for St. Louis, same is true for Dallas. You can measure the increase of all cities because we dissipate heat in cities. That's a measurable phenomenon. Nobody worries about it, but it's measurable. I don't want to minimize it. It's real, but I think it can be cared for.
So as far as reactors, getting back to the reactor design, you say the heat exchange method for the reaction chamber is conventional heat exchange.
The first loop is actually a liquid helium, and and that has to exchange probably to a working fluid of either sodium potassium metal or to a high-pressure helium. I don't think we should put high-pressure helium inside the chamber for fear that if a small leak occurs, you destroy your vacuum and therefore stop the operation. You don't want to, you want to anticipate problems that your heat exchange might cause. We see it that there are two stages to the heat exchange. One internal to the envelope that the lithium is contained within, and the other one external to that envelope. And that external heat exchange could be, very likely would be high temperature or high pressure helium gas, as has been proposed by GA for the advanced nuclear reactors.
So the idea is that the heat gets initially captured in the lithium gas, which then interacts with the walls.
There's about
that
50
then-
tons of lithium circulating inside that chamber, and its auxiliary storage and vacuum pump facilities. It's a complicated beast.
So-
I don't want to minimize the complications of that chamber, but they've all been looked at and worried about in 4 different versions, and I think that that's something that the engineers will solve without a problem.
I'm sure it's been looked at very carefully. I only ask these questions because I'm curious.
Well, I'd be happy to talk with you about the details, but if you want to stick around for a minute or two afterwards here.
One of the comments that has not been made, that I think really needs to be made, and that is that there have been a couple of articles in Physics Today that have come out, and one of them in June and the last one in October, that talk about this process as being doable within the near term. And that's from a science-based position, separate from the promotion of the energy source.
I would recommend, that's a good point, Hal. My brother, Harold Helsley, in case you didn't get introduced to him, I don't know whether you even got introduced to me. I'm Charles Helsley. But anyhow, let me finish that one. Physics Today, June, in the letter section, and Physics Today, October, letter section, first letter, give you an update on some of the older thinking on this kind of fusion reactor. And if you want to look up more, look up a guy named Sharkov, Sharkov. He's a Russian, Boris Sharkov. He has a very nice write-up about the program that's going on in Russia. Yes?
I wonder, where would you build this ideally? Like in the desert where land is cheap, or in the Antarctic where it's cold, or
If I
right
had
in the middle of Los Angeles?
If I had my druthers, let me answer it, my druthers. I would build it at Camp Pendleton. I supply fuel to the military. Military needs strategic source of fuel. They have a piece of land that's not being used. It's all underground in tunnels. You'll never see it. And one of my reactors would be the San Onofre site, which would replace a nuclear reactor with a fusion reactor. The other 4 sets of reactors would be at other points down the coast. You would see 4 all you would see driving down the highway is 4. I want you to visualize what it is, you see. It's 4 San Onofres several miles apart, each cluster several miles from the other one. And there's going to be some auxiliary business around that in terms of generating this hydrogen. But that's what you're looking at.
Cool.
And that's a very good site. Why? Because it has ocean water. Now, my second druther site, there's a great place for it, just south of the Canyon Diablo site. Beautiful place to build another 4 or 5 reactors, and you would not damage the landscape, whatever. I've actually taken the Canyon Diablo and just planted it 4 times down the coast, and you would never know that they were there in terms of the ecology offshore and so forth. If you want to go to the desert environment, yes, great place to be Nevada test site, except it doesn't have any cooling water. I'd have to use air cooling. I'd rather not use air cooling at that location for the simple reason I don't want to increase the rainfall in Salt Lake City for fear I flood the airport. I mean, there are serious, that's a joke, but it's a serious issue.
The other side he didn't mention is Hawaii.
I actually worked out it for Hawaii. Hawaii is actually the most energy consumptive per capita place in the world. Hawaii thinks of itself as being totally green. It's not. We use more fuel per capita than any other population in the world. Why? Because we fly all of our industry in and out of the state in the form of tourists. And that jet fuel is a very expensive item. 1 million people, we have a fuel bill of $8 billion for 1 million people. That's Hawaii. And it turns out you can put one of these there and it will produce all the fuel you need and export fuel to Los Angeles. California doesn't like nukes, and so it's going to be hard to build them here. We may wind up building the first one. We may wind up building the first one in Idaho for the simple reason that they have permitted land that you can put experimental reactors on. Anyhow, not where I want it, but that's where I might have to put it. There are many other places. There's a strong interest right now to put one in Florida. There's a strong interest to put one in Spain. There's a strong interest to put one in Egypt. High population centers with no source of indigenous energy. They can't afford the energy bill. They'd like to have something that provides them the energy. That may be where it goes. India is very interested. China, less so, but I think because they're going to try to do it themselves.